Okay, so there are some questions which I was dealing with last few days. I'll also give that, and based on the knowledge of whatever you have till now studied, like forces and field, you should be able to solve that. Of course, the concept of potential energy and other things you will be studying afterward. It's not a big deal, but with whatever knowledge you have, how can you take the approach to solve a question? And this is a very good question. Let us try that. Question number one. Suppose this is a charge q and this is a charge small q. This charge is fixed and this distance between this is a. This charge is free to move and it is released. It is released. When this charge is released at this point, it starts moving due to the force of that charge. That charge is not going to move because it is fixed. So what happens is that this charge starts moving and its distance changes. Initially the distance is a. Finally, after some time, this charge goes here and now the distance has become b, and this is now having some velocity, right? This charge is now having some velocity. It is having some velocity. Now you need to find out what is that velocity. Okay, you need to find out the velocity of this charge. How will you try this? This charge is fixed. You can take the masses also. This charge has mass small m. This mass of this charge is small m. This mass, if you want, you can take it capital M if you want it. Okay. So let us derive a formula. We can of course substitute values and calculate, but we can try to derive a formula. Why formula is important? Because a formula can be easily substituted with values and a result or answer can be calculated, and particularly for competitive exams like NEET or JEE, where you have to solve questions within a minute, you are supposed to know the formula. How you know whether you have knowledge or not, that is secondary, right? The primary thing is that do you have the formula for this or not. If you have formula, you have to do substitution, and if you're good at calculation, then immediately within few seconds you will get the answer. Of course, how the formula is coming, that is the main thing, that is the knowledge. So we should have that knowledge, then these formulas are, you can use it. Okay, so let us try that. How do you calculate the speed of this particle? It was released here when the distance was a. Now distance has changed b. What is the speed? How do you solve it? Try that. Take few minutes and attempt it. What will be your approach? Can you tell what will be your approach? How will you solve it? Yes, Kevin? Yes. Acceleration. Hmm. What about the electric field? Electric field is constant or changing? How it is constant? Because the fixed charge is creating the electric field, and the distances are changing, right? So this small charge particle is moving and its distance is continuously changing. Initial distance is A, final distance is B. Hmm. So electric field is not going to be constant. Electric field will be also changing, right? So the acceleration of this particle will also be changing, right? Na? Yes, Kevin. So acceleration will be changing, and acceleration will be changing with distance. So if you know the acceleration, then you can think of writing the differential equation. Yes, acceleration can be written as dv by dt or v dv by dx. I think here you can use v dv by dx, right? Yeah, that is the approach. That's right. Correct. Then after that you can use integration solve. That's the right approach. So suppose if you apply that, so let us say at any instant you need to see. Let us consider the charge particle at some instant here at a distance of x. Then the force which is acting on this is like this way, and this force is, you can directly calculate force as k q1 q2 by x square. Okay, so k capital Q small q by x square, and force is mass into acceleration. So acceleration, let us write acceleration as just acceleration, force by mass, so k q q by mx square, and acceleration now I can write as v dv by dx, correct? K q q by mx square. Now v dv I can write as k q q by m dx by x square, and then I have to just do integration, and it's the game is over now. After that integration, initial velocity released means 0, final velocity is v. Initial distance A, final distance B. Limit we have to just substitute and do calculation. So this is v square by 2 is equal to kqq divided by m. 1 by x square integration is minus 1 by x, is going from A to B. So v becomes, after substituting, root under 2kqq by m minus 1 by b minus minus plus 1 by a, so 1 by a minus 1 by b. This is the result. This is the answer. Yes, are you clear about it? Yes, tell me. So to solve this question, you need to have some, approach. You have to attempt it, huh? And you need to definitely think about it. So solving question is not easy. Everything, every step requires thinking. So if you start thinking, then only you can move forward. And I will try to correct your approach wherever you can make mistakes. So you need to try. There can be another approach also. Another approach can be work energy theorem, but work energy theorem is basically this only, because work energy theorem is derived from the same approach. Okay, so either you use this or use work energy. Work energy theorem means work done, the change of kinetic energy. So work done you have to calculate by integrating, because force is a variable force. So integration of f dx you will do, that is nothing but half mv square, and from same thing will come. So work energy theorem you use or you use kinematics concept, same answer will come. Approach are almost same. Now what will happen, suppose, see, this question was asked in the exam, and some people said that this question cannot be solved because we have to learn the potential energy concept and then only I can solve. What nonsense it is! What potential energy is being used and how much big calculation it is. Is it a big calculation? It's a so simple calculation and within few steps you can solve it. We should not try to impose on the student that when you learn this then only you can solve it. No, you already know things. Only thing is that you have to explore, you have to think. A big questions can be also solved from fundamental methods. Only thing is that sometimes if you are going by fundamental it may take few steps more, right? And if you use some results of potential energy or energy conservation, it can be solved within few steps. That's all. Maybe here let us say 5 steps are there, maybe there you can solve by 2 steps. But the method, what is important is there, are you able to use the fundamentals or not? That is important. If you are only depending on the formulas and this thing that thing, okay, use the formula, but you should know the fundamentals. Now I will give a question, same question. Let us keep this charge q not fixed. Let us say that this charge q is not fixed, it is also moving, it is also free. Okay, now the question is modified and try this question now. So this charge q is also free to move, and this small charge q is also free, both are free. This is also free, this is also free. Initially the distance is a, now finally they are moving, so finally the distance become b, the separation has become b. Okay, now the question is, let us say that it is right now moving with a velocity v1 and it is moving with a velocity v2. Can you calculate the velocity v1 and v2? You can take the masses. Already I told this mass is small m, this mass is capital M. Initially is released means initial speeds are 0. This is 0 speed, this is also 0 speed. Now how will you apply that? Yes, can this same approach work? Hmm? They will have different acceleration. Can we apply the same approach? Hmm. Huh? Delta p equal to, but it is changing now. The momentum is also changing with time. Yeah, differentiation will come, but the thing is that how it will come, that is different, because both the bodies are moving. So you have to study one body with respect to other, right? You cannot study separately, because if you study separately, then how do you take distance? But distance what you are taking is the distance between them, which is nothing but the separation. That means you have to study one body with respect to other. Relative motion you have to study. So the same concept can also be applied by using relative motion. Let us try relative motion and see the result. So relative motion, when you see, that means you have to study one observer, you have to keep, let us keep observer here. So if you say that this is the observer, then relative to this you have to study. So this observer will see what? This observer will see right now this body has a velocity of v1 plus v2, because they are going in opposite direction, right? So it will give its relative motion means opposite direction means it will add up. Hmm. So when you are going to do the same thing, but the force, what force is going to see? Force. Or what acceleration he will see, because it is also accelerating, this is accelerating in this direction and this is accelerating in this direction. So relative acceleration will be relative acceleration will be a1 plus a2, because acceleration factors are also opposite. So relative acceleration, and this is relative velocity, which you can write as vr. So relative acceleration is can be written as v dv by dx, where this v is relative velocity and x is the separation, relative position. Now you can apply that. What relative acceleration is a1 plus a2. A1 is what? Force by mass, force by mass. Force is same, right? Same force. So force by mass m1 plus force by mass m2, right, is equal to vr dvr by dx. Okay, force I can take common, or 1 by m1 plus 1 by m2 will come out. Then force is coming out common. Force, now you write k q1 into q2 by x square. Vr dvr by dx. So again you try to solve it. Bring one side this k, this factor, this factor will be coming 1 by m1 plus 1 by m2. 1 by m1 plus 1 by m2 is a constant. K Q Q is also constant. So dx by x square will be there, and this is v dv. V is vr. Now you do integration. While you are doing integration, constant is coming out. Okay, so do integration. And relative velocity, initially both have zero velocity, so initial relative velocity is zero. Finally the relative velocity is vr, which you know it is v1 plus v2, and initial position is a, final position is b. Separation. Now you do this integration, what it will come. This factor is constant, 1 by m1 plus 1 by m2 into kqq. 1 by x square integration again is 1 minus 1 by x, and minus 1 by x is 1 minus 1 by b minus minus plus 1 by, so this will give 1 by a minus 1 by b factor after you put it, and this will come v square by 2, so vr square by 2. Okay, right. So from here relative velocity square means relative velocity you can calculate. Relative velocity will be root under 2 times, yes, 1 by x square integration is minus 1 by x. Okay, minus 1 by x. Now you substitute upper limit. So minus 1 by b minus of minus 1 by a. So which will come minus 1, 1 by a minus 1 by b, right? Okay, so do that. How much you are getting? 1 by a minus 1 by b. Correct. This is relative velocity you have calculated, which is v1 plus v2. So that means what you have calculated right now is v1 plus v2. You have calculated v1 plus v2, which is root under 2 times 1 by m1 plus 1 by m2 into kqq 1 by a minus 1 by b. But we want v1 v2 both, or you want v1. So you need to eliminate v2, you need one more equation where you will get the another equation. Yes, you need one more equation. Any idea how will you get the other equation? Note that if you take both the charges as a system, then the forces are internal forces. There is no external forces on the system. So when the external force is zero, what principle can you apply? Yes. When external force is zero on a system, what can you apply? You must know this. Yes. All such problems you have studied. Explosion of bombs, collisions. All this is based on this principle only, na? Yes. What is that? Huh? Yes, Kavin. Delta V, delta P. Momentum is constant. What is that called? Forgotten. Conservation. Conservation of linear momentum. Yes. Do not forget this. It is a very, very important. Whole chapter is based on this, concept. So when external force is zero, the center of mass has same momentum or same velocity which it was having initial. So initially system was at rest. So center of mass is zero velocity. So momentum is conservation. M1 V1 is M2 V2. They will cancel out, right? So you got the another equation M1 V1 equal to M2 V2. So V2 you eliminate now. V2 will be M1 by M2 into V1. So substitute this and try to solve. So V1 plus V2 has become M1 by M2 into V1 is equal to this side same term. Should take V1 common. Take LCM M2 plus M1 by M2 is this same term. Okay. Now you take out V1. So this term you will be taking that side. So V1 will equal to this term will go that side. So M2 by M1 plus M2 will go that side, and you can take inside the root. That means it will become square. So M2 by M1 plus M2, you can take a square of this inside, and this term will be there. To here LCM you can take. So M1 plus M2 divided by M1 M2 into this term will be there. KQQ 1 by A minus 1 by B. So from here you got the answer. Now little bit simplify. That's all. So V1 is equal to root under. This will 1 M2 got cancelled, right? So you got M2 divided by M1. 1 M1 plus M2 also get cancelled. So M1 plus M2. That's all. KQQ 1 by A minus 1 by B. Clear? This is speed V1 of the first body, and then V1 you can substitute here, you can get V2. Clear? Yes. So any question can be solved from fundamental level. We should have this idea. Now, of course, when you have the when you will be studying the potential energy, this can be solved within few steps. But we should know about these approaches because these approaches are fundamental approaches with which you can solve a complex question also. Another thing is that how can we solve this question using work energy theorem? Work energy theorem. So how will you calculate work done by the forces? Because you know work energy theorem. What is work energy theorem? You know that. So work energy theorem is a very, very important concept. Work energy theorem. Work energy theorem says that the net work is change of kinetic energy. So here you have seen these two particles having charge q and a small q, right? And initially they have zero speed, so they have zero kinetic energy. Finally they have kinetic energy, so half m1 v1 square plus half m2 v2 square. Okay, this is the final energy, that is the change of kinetic energy and work done. Now the electrostatic force which is acting, this force acting on both, so this electrostatic force is acting here, this electrostatic force is acting here, and the distance is changing. So you need to calculate work done on both the body due to electrostatic forces. So electrostatic force is doing some work on this body, same electrostatic force is doing some work on this body. You need to add both the work, and then of course momentum conservation you have to use, so you can eliminate v2 and then you can solve. But the question is to calculate this work done, no, using the concept of work done. You can try, but there you will learn a lot of things. Today I learned many things from this, although I could not do that because I can solve it by using potential energy. But if I not do this no work calculation, I will not understand how to calculate work. Many situations calculation of work require the concept of work done by integration. You try that, I am leaving up to you. You can try to calculate work done due to these forces and then try to do that. Okay, you'll get the same result if you do correctly. Okay, but generally, not generally, almost many people, 99% people will make mistake in calculation of work done. So you need to think about this. Okay, so you will be able to solve questions like this. Are you clear about this? Yes. Okay, so then we can move to potential energy. Now it is a good time to take potential energy, potential concept. So let us do that. Electric potential and potential energy. Again start with a source charge. So this is a source charge. Source charge. Source charge. So source charge has created a field around it and you want to bring some charge near it. Remember, if there is no charge near this, that means that does not mean that no charge is there. Charge may be present at infinity because infinity is something which nobody knows, right? So right now this charge will say that there is no charge near me. That means same that there is some charge at infinity. So now suppose I want to bring that some charge which you are calling as test charge. So a test charge we are bringing from infinity to some point. Let us bring some test charge from infinity. This charge is test charge and you are bringing it at some place, right? And now the separation is, let us say, r. R is the separation. Initially this is the separation, means it is x, and initially the separation, this x was infinity because it was very far away. So you want to bring this charge from infinity to this point. So what is potential energy defined as? Potential energy, electrostatic potential energy. Okay. Electrostatic potential energy is defined as the work done work work done by which force? Work done by external force. This you note, very important. Work done, always when work is done there is some force which is doing work. So work done by external force in bringing a test charge from infinity from x is equal to infinity to x is equal to r. This is called electrostatic potential energy. Okay. So if I write equation for that, that is simply means this potential energy is equal to the work done in bringing charge from infinity to that point. This is the work done. Actually, this is not just the work done, it is actually the change of potential energy. Note that. Generally, this is the change of potential energy, which means potential energy of that place, which you write as potential energy at R minus potential energy at infinity. Okay, this is what it is. This is what is the work done. So, work done by which force? Work done by external force. This is external force. So work done by external force from bringing from infinity to this location is nothing but change of potential energy, but by assumption we are choosing potential energy at infinity to be zero, but note that it may not be zero. Okay, so potential energy at infinity, the potential energy at a location will be work done in bringing to that location plus the potential energy at infinity, but by convention we are choosing potential energy at infinity to be zero. So if you consider this term to be zero by convention, by convention, then the potential energy at that location, potential energy at that location is nothing but work. Okay, so work done, we have just now seen how to calculate work done. We can do calculation. Okay, and also note that potential also definition you note here. We have seen the definition of potential energy, same place. Now you see the definition of potential, electrostatic potential, electrostatic potential. So electrostatic potential, which is represented by the symbol V, so it is the work done per unit test charge, work done per unit test charge by external force in bringing the test charge from x is equal to infinity to x is equal to r. Okay, that means what? This means this is saying that work done per unit charge, work done per unit charge means this work done which we have calculated, right, divided by test charge. This is again potential, which is not exactly potential, it is the change of potential, which again same thing you can write. Change of potential means potential at that location minus potential at infinity, because you are bringing from infinity. So this is the work done, right, by q. This can also be written as potential at that r is equal to work done from q to r by q plus potential at infinity, but now again same point, potential at infinity we are going to assume to be zero by convention, so potential at a point will be equal to work done in bringing the charge from infinity to that point. Okay, this is infinity, from infinity to that location, so work done in bringing the test charge from infinity to that location divided by that charge q, which can also be written as potential energy by charge. So all these definitions are there, but now the main thing is, you can see in all this formula, main thing is work done in bringing the charge from infinity to. Let us calculate that work done. Okay, then we can write these formulas. So work done calculation we will do quickly. Here in this diagram we have seen. So let us See, at an instantaneous location. So at an instantaneous location, this test charge is here right now, and right now the distance is x. Note here, very important thing is that this test charge you are bringing toward the source charge. So dx is going to be this side. Note that dx is going to be the left side, and this is the instantaneous position, right, which I have already drawn here. This is the instantaneous position. So tell me, is the distance x is increasing or decreasing? What do you think? X is increasing or decreasing? Yes. Kavin, Chatris, is the distance increasing or decreasing? Huh? Decreasing. Decreasing. So because the distance is decreasing, you have to use minus dx. Because the distance is, so wherever you are using dx, you have to use minus dx. This is very important. Okay, because distance is in. So now when you calculate work done, let us try to calculate the work done. So work done, when you calculate by external force, remember work done you have to calculate by external force. So external force will be acting like this. Let us say that is positive charge, so electrostatic force will be acting like this, and external force must be acting in this direction. So external force is acting opposite of electrostatic force. Okay, so we can say that work done is equal to integration of external force into dx. Can we write it? And external force we should write as minus d. External force is opposite of electrostatic force, so external force we have to write as minus of electrostatic force, and this dx is also we have to write as minus dx. Note that. So this we are going to write as minus of electrostatic force, and this is minus dx. So both minus minus becomes plus, right? Plus. And electrostatic force formula, now you write 1 by kq q by x square, kq by x square, right? And that is dx, and integration of this. Now check out this. What do you get? Infinity to that point also we need to write it. So I think we'll not get the proper sign. Huh? Work done by external force we have to write. So external force, and this minus dx is in this direction. Correct, only external force is negative. Negative direction. No, here only somewhere mistake is happening. See, so actually what it is, what is the force? Force is dot product. See, here we need to understand very clearly. Force is the dot product. So external force dot dr vector we will write basically. Now let us write this as magnitude of external force, and this dr, and cos 0 degree is 1, right? Cos 0 degree is 1. Now this dr we have to write this as, this dr we have to write this as minus dx. This is what is important, because dx itself is negative, dx is decreasing, so dx is negative, so we have to put it minus dx. Are you clear about this? Yes. This is very important, because in the textbook they don't make these clear points. They simply write the final step and then they just do. But this we have to write because it's a dot product. So magnitude of force, magnitude of this displacement, cos 0 degree is 1 because both the forces are in same direction. This minus dx which I have written, that is what is dr. Note that this minus dx which I have written it, that is what is dr, right? Dr vector it is. So this direction is minus dx, this is force, right? Now you do it. Now, remember this is magnitude of external. Now you should not put at minus. Now we should not put as minus. We should write magnitude. So now write the magnitude of force. So it is kqq by x square and minus dx will be there, right? Now you integrate. Do the integration now. So when you are doing this, you will be getting as kqq minus is there, and 1 by x square gives minus 1 by x. This minus and that minus will become plus. So you get 1 by x as plus, and then you take limit. You are taking limit from infinity to that r, right? Limit is infinity to that r. Now you will get this result. So after you substitute it, what do you get? You get the formula for work done. So work done in moving from infinity to r by external force is kqq. 1 by r you will put, 1 by infinity is 0. So we are taking this as work done. So once you get this work done, this is the formula for potential energy also. So now you know the potential energy formula. Potential energy formula is kqq by r. R is the distance between the two charges. So if two charges are separated by distance r, the potential energy between them is k q1 q2 by r. And potential formula just substitute here, work done by q. So work done we have already calculated, substitute here, right? So substitute in this formula, work done is kqq by r divided by small q. Q get cancelled, so potential at that location is k q, small q get cancelled, so kq by small r. This is what. Remember, this result is only true when you are ignoring potential at infinity. Similarly, the formula for potential energy kqq by r is only true when you are ignoring potential energy at infinity, because when you are taking infinite distance there is no interaction between them, right? But sometimes in the question they say that potential energy at infinity is there, then you have to add that term, you need to add that term. So the same formula will be there, plus potential at infinity you have to add, whatever they will give, that you have to add. Clear? Are you clear about this? Yes. Okay, now let's understand this relationship relation between field and potential, and also relation between force and potential energy. So these two relations go side by side. Let's understand that. So we should know that the field is given as minus del vector of v. And what is del vector? Where del vector is partial differentiation dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. Similarly, exactly in the same manner, this force vector will be minus del vector of potential energy. Where have you studied this? Can you tell me in grade 11 where have you studied this? Yes, Kavin, right. In work energy chapter, you have studied this because this force is conservative force. conservative force. So for any conservative force, we write like this. Okay, and you have seen also what is partial differentiation. So this relationship is there, but for one dimension, you may write simply as is minus dv by dr also you can write, or dv by dx also you can write. Okay, like this we can write it for one dimension, or sometime we can write this e as minus dv by dr. Dr also you can write. R is the direction along radial direction you are taking. Otherwise, this is like the component. If you take like this can be like component along x-axis. If you are taking one dimensional, 1D. For 2D, 3D, you can use partial differentiation. Same manner here also, force you can write as minus du by dx or du by dr. Force along the x-axis we can write like this, because if there is no other, no, so one dimensional we can use this. Okay, so this is an important lesson. Now the reverse relationship is also important. What is reverse relationship? Reverse relationship is like change of potential dv. dv can be written as minus e dot dr. This we have to remember. This is dot product here. Similarly here also du will be equal to minus f dot dr. Okay, so the change of potential is equal to minus E vector dot dr vector, and change of potential energy is minus F vector dot dr vector. That F is any conservative forces, like here it is electrostatic forces, conservative force. Okay, so now based on this, there are some important results that we can note here from this formula. If I integrate this one, so integration of dv, which is called delta v, integration of dv, that will give us in minus integration of E dot dr. So in many questions you can find out the change of potential by doing this. Okay, change of potential by doing this. Also here also the change of potential energy is integration of du, which you can do it by minus f dot dr. Now note here that this is a conservative force, so integration of work done by conservative force, this is nothing but work done by conservative force, integration of f dr, this is conservative force, so this is nothing but minus work done by conservative force, So you can also say that work done by conservative force, is minus change of potential energy. Work done by conservative force is minus change of potential energy. And work done by external force, is minus work done by conservative force. So it will be equal to plus change of potential energy. Okay, so these equations are important. Sometimes these equations comes in an assertion reasoning based questions like that. And in all this process, note very important thing, in all this derivation which we have done it, we have slowly moved the test charge. Note, this is a very important thing. If you want, you can write that word in the definition also, that the test charge you are bringing slowly or gradually. This definition which we have written here, where is that? Previous slide. Like in the potential by external force in bringing the test charge from this to this, Very, very slowly. Add this word very slowly. Very slowly means you are almost moving with zero speed. So this word you can add in the definition, then only it will be correct. Very slowly. Very slowly. Or gradually. So why are we saying like this? Because if you are slowly you are bringing, then you are not increasing kinetic energy. Correct? You are slowly bringing, so you are not increasing kinetic energy. Otherwise, if kinetic energy is changing, then you have to apply work energy theorem. Now let us consider a different definition. If you are speeding up, when you are bringing it, you are, let us say, speeding up. So if you bring a charge, let us say if you move a charge from this point 1 to this point 2, this point to the same charge you are moving, right? And there are some field due to some source charges. So if you are moving it and you are changing the speed, that means here its speed was v1 and here its speed is v2. So what are the forces acting on it? First of all, you are applying some external force, and some electrostatic force is also acting. These two forces are there, okay, and any other forces may be there. So you have to apply work done. Net work done is change of kinetic energy. Change of kinetic energy. So basically, work done by external force plus work done by conservative force. Conservative means electrostatic force. That's a conservative force is equal to change of kinetic energy. And work done by conservative force, we have seen it is minus change of potential energy. That is how the conservation work done by external becomes change of kinetic energy plus change of potential energy. So now you can also say that it is like the change of total energy. Change of total energy. Remember, this change of potential energy is not the gravitational potential energy, because if this is gravitational potential energy, then change of kinetic energy plus change of gravitational potential energy become change of mechanical energy. That is the conservation of mechanical energy. But here this is not the gravitation potential energy, it is the electrostatic potential. Suppose if gravitation force is also acting, then you have to also put here work done by gravitational force, and work done by gravitation is minus change of potential energy, which will also come here. So basically it is this total change of energy, okay, whatever energies are there, total change of energy. So that is what it is, work done by external forces. So external force work done will be the change of total energy. So work energy theorem is a very powerful technique, very powerful tool to solve any type of question, whether energy is conserved or not. You can always apply work energy theorem. If you have any confusion, always apply work energy theorem. There may be spring force, there may be gravitation force, there may be this force, that force. You just add work done by first force, work done by second force, work done by third force, work done by fourth force. All work done is equal to change of kinetic energy. But their misconception can be that work done by net force. Remember, work done by net force is not the same as the total work done. Here in work energy theorem, it is the total work done. It is not the work done by individual, means it is the sum of work done by individual forces. It is not that it is work done by net force, because net force is a single force which is the sum of all forces. And if you calculate the work done by the resultant force, that is going to be different in many cases. That is why work energy theorem is this is the sum of all the work done by this plus work done by that. Are you clear about this? Yes. Okay, okay. So this is now you approach that question, that question which in the beginning I told. Now you can solve very fastly. Okay, how will you solve it? Let us say that this was the charge q1 and q2, and let us say initially it was having zero speed. Now this charge q1, or one was capital Q, another was small q, right? One was capital Q, another was small q. Now this capital Q has V2 and this small q has V1. So apply energy conservation, right? There is no no external forces on this system. Momentum conservation will definitely be there. So this mass and m1 v1 m2 v2, this will be there. Momentum conservation. Now energy conservation, if you apply that, the total energy initial and total energy final are equal. So total energy initial is what? Initial distance is a, final distance is b. So initially we do not have kinetic energy, we have only electrostatic potential energy. And what is electrostatic potential energy? So total energy initial is equal to total energy final. Initial energy is only potential, so k q q by distance is a. Final kinetic energy is also there. So half m1 v1 square plus half m2 v2 square. This is final kinetic energy plus potential energy k q q. Distance has become b. That's all, over. And now substitute v2 in terms of v1 and solve v1. Clear? Yes. You can just substitute from here and you can just solve it. It will be just a very small thing. So from here k q q you take common, k q q. So 1 by a minus 1 by b. The loss of potential energy is converted into gain of kinetic energy, half m v1 square plus half m2 v2 square. You substitute v1 square into m1 square by m2 square. So from here you take half m1 v1 square common. This will become 1 plus m1 by m2, right? So from here v1 becomes root under this is 2 times, and you take that m2 by m1 plus m2 will be in the denominator, m1 plus m2, and this is k q q 1 by a minus 1 by b. See, we have got the same result but with a different approach of potential energy concept. Are you clear about this? Okay, so we will be now applying work done in all the questions. So whenever they say what is the work done, means work done by external force. Suppose they say what is the work done in moving this charge from here to here, that is nothing but work done by external force. Okay, so like that we can do all the calculations. So finally let us summarize it. Summarize means you can write change of potential as change of potential energy per unit charge, or it is nothing but work done per unit charge. So sometime from here work done can also be charge into potential difference. Okay, or work done is change of potential energy. This is all about external. Remember, these are all external due to external forces. External forces. So many questions will be there. So what type of questions will be coming? They will say that, let us say this charge, this charge, this charge, 3 charges are there, q1, q2, q3. They are separated by some distance, let us say r. They are on the equilateral triangle. What is the work done to move this charge to infinity? What is the work done? Work done to move this charge to infinity is nothing but the change of potential energy. So what is the potential energy of this system right now? And when they go to infinity, the potential energy of system will become zero, because infinite distance means they will not interact. So basically, if they ask work done means, change of potential energy, final potential energy minus initial potential energy. Here if you have to separate them to infinity, so final potential energy will be zero. That means you have to calculate minus of initial potential energy. Now what is initial potential energy of this system? If you have to calculate the system, means you have to take pairwise. Like for example, the initial potential energy of this 3 charge system is charge 1 and 2, charge 2 and 3, charge 3 and 1. That's all. Okay, So you have to write u12, u23, u31. You have to take pair of 2, 2, 2, 2, 2, 2, two different charges, right? And this u12 will be same k q1 q2 by r. This will be k q2 q3 by r. This will be k q3 q1 by r. All the distances are same. This is the initial potential energy of system. Substitute minus sign with that, it will give the work done. Clear? Any doubt in this? Okay, so now you can start working out basic level questions from NCRT of potential and potential energies. There are a lot of questions will be there. Go through solved example and see NCRT questions, and I will be also sending worksheets on that. By the time you can start worksheet 2 and 3 on forces and field. Okay, and tomorrow you can write test. I will set the paper today itself. Okay, by the I was not having time, a little bit busy, but today I will be setting the question on forces and field. Okay, force and field question I will set tomorrow. You don't have class, you can write the at your free time, you write that. By tomorrow you write it, then we'll start this solving questions on potential energy and potential. Clear? Okay, then we'll see next class. Bye bye all.